Hey everybody, welcome to another exciting installment of real variables slash advanced calculus slash possibly going into a little bit of basic calculus if you're paying attention and you need a different level of understanding of basic calculus 2020. So anyhow, we're going to talk about the fundamental theorem of calculus today. All right, and so in our textbook this is 5.3. And that's really weird. I don't know how that happened, but so in our textbook, this is 5.3. I'm not in red, I'm in black. Thank you. The fundamental theorem of calculus. And let me just state it out for you. Remember, the fundamental theorem has two parts to it, 1 and 2. All right, and so f is a function that goes from AB into R. And so the first part of this theorem says that you've got a couple of basic hypotheses. If f is continuous and we define big F of x to be the integral from a to x f of t dt on all of AB, then what we can tell you, because f is continuous, this integral obviously exists, all right? And so all we can tell you is that f is a member of the continuously differentiable functions over AB, right? Remember, script C1 is the space of continuously differentiable functions on the set AB, on the closed interval AB. And when you differentiate with respect to x, if we differentiate the integral from a to x of f of t dt, right, you just get f of x, right? And so by definition, obviously, this is also known as f prime of x, and we'll use that in the proof, okay? Big F prime. And then the second part of the fundamental theorem, this is true, and this is true, of course, for every x in AB. Okay, or I should just say on AB, whatever. You get it. All right. So part 2 says if f is differentiable, okay, on the entire closed interval AB, and we, normally we'd have differentiability defined on the open interval, but here we need it on the closed, so we're talking about one-sided derivatives from the left and the right at A and B. And if f prime is integrable, so just because you're differentiable doesn't mean you're integrable, your derivative is integrable, all right, because it could turn out to be a mess, all right, but for anything that we would come up with, typically we would not have this issue, but just to be precise, if f is differentiable on AB and f prime is integrable on AB, then when you integrate from A to B f prime of t dt, then you simply evaluate it f of b minus f of a, right? And that's what we are used to thinking of the fundamental theorem of calculus. This is what we used in Calc 1, right? That's what we thought of as the fundamental theorem of calculus, but really there's two of them, and we need to prove this one first in order to prove the second one, okay? So before we go any further into the proofs, I want to remind you of a few things we need in order to do these proofs, okay? For the first part, for the first proof, we're going to use, from, again, the numbers from our textbook, Theorem 516. And Theorem 516 simply says the integral from a to b of a constant dt is the constant times the length of the interval. All right, and there's lots and lots of ways that you can show that to be true. You can show it graphically with the area of a rectangle. You can show it using the basics of the limit definition of the Riemann sum, upper sums and lower sum. There's lots of ways to do it. All right. So just trust me on that. Theorem 520, we're going to use that. And Theorem 520 says for any point in between A and B, if you want to take the integral from A to B of f of x dx, then you can do that by breaking it up at c. You're allowed to break it up at c. Again, this is assuming that this integral exists, right? But if I write it, it's assumed to exist. So, and I'm summarizing the theorems for you. I'm not writing them out. You can look them up and find all the hypotheses and stuff for them. All right. And then theorem 522, all right, is our, basically it's kind of a triangle inequality for integrals. It says the absolute value of the definite integral is less than or equal to the definite integral of the absolute value. All right, and this is obvious because this is always greater than or equal to 0, where this might have some negative area, and so when you add them together, they cancel out. There's some cancelization there. Here, you're always going to be above the x-axis, so that's got to be bigger. All right, so anyway, those are the three main theorems we're going to utilize for the proof of part 1. And so we'll go ahead and do the proof of part 1, and then we'll talk about part 2 and how that's going to go. So the proof of part 1, remember that part 1 is the one where we're going to differentiate this big F. We're going to differentiate this integral defined function. Function defined as the definite integral. Okay, so we want to show what? We want to show that the derivative is equal to that. If we can show this, then this part's easy. All right, because you found the derivative and then showing it's continuous, well, it equals f. F is continuous. So this part, there's nothing to show, really. Here is what we got to do. So we're going to differentiate, and we're going to use the limit definition. Okay, so what's the limit? If we want to find, let's just pick a random x in our interval. All right, and I'll call it x sub 0 to be specific. Let x sub 0 be an AB. And granted, if it's one of the endpoints, guys, we're going to have limits from one side or the other, but it's enough for us to think about just, the one-sided limits overall. And so we're going to take a look at the definition, if it exists. What would the definition be? The definition of this would be the limit as h approaches 0 of big F of x sub 0 plus h minus big F of x sub 0 all over h. Okay, so that's what it would be. We're going to do one-sided limits to kind of make life a little easier on ourselves. So we're going to take it from one side. If we can do it from one side, we can do it from the other, right? So this would be technically the right-sided derivative, but whatever. Okay, so let's take a look at this limit. Okay, we're going to work with the definition here. So big F of x sub 0 plus h is equal to the integral of from a to x sub 0 plus h of f of t dt, and big F of x0 is the integral from x sub 0, sorry, from a to x sub 0 of f of t dt. And so when you subtract these two, because we're looking at h positive, this is one of the reasons I'm using positive h, so that I know this one's bigger, because h is positive. So if we look at the difference between these two, you end up with the integral from a to x sub 0 plus h of f minus the integral from a to x sub 0 of f. And so using theorem 516, no, it was 520, right? This breaks down to just be the integral from x sub 0 to x sub 0 plus h of f of t dt. Okay, so this is the theorem we talked about here, where, oops, up top here, 520, that says if you're integrating from a to b, you get integral from a to c, c to b, right? So what we did was, this is the integral from a to c, this is the integral from c to b, and here's the integral from a to b. All right, so we just did a little bit of algebra and took this to the other side. So we end up with this is equal to the difference up here. All right, this difference right here is equal to this. Okay? So, we know that f is continuous. That was given. And so we know it's continuous at x0. If we let epsilon be greater than 0, there exists a delta greater than 0 such that, and again we're working with x0, h being a little bit positive this time, so t minus x0 less than delta implies f of t minus f of x0. These still have to be in absolute values, and that's less than epsilon. Okay? So we have these two pieces. We have this information, and we have this information right here. So what are we going to do with that? All right, so using Theorem 516. What's 516 again? 516 is the theorem that states that the integral of a constant is the constant times the length of the interval. All right, so using 516, if we take the integral of x sub 0 to x sub 0 plus h, and we integrate f of x sub 0, that's a constant, right, dt, what do we get? We get f of x0 times x0 plus h minus x0, and the x0's cancel and you just get h times f of x0. Okay? So, if we take this h to the other side, then we get f of x0 equals 1 over h times this thing. Okay. And now we're going to look at the difference between this difference quotient and what we want it to equal, which is little f of x0. That's why I wanted to characterize little f of x0. Okay, so we have, let's continue to the next page. All right, so we have the absolute value of the difference between the difference quotient of the big F at x0 and little f of x0. We're gonna examine the difference between these two, because if we can make these very, very small, then we're set. All right. Well, this is equal to 1 over h times the integral from x0 to x0 plus h of f of t dt. Right, this part. That part right there is equal to this. Right, because the definition of big F. All right. And then that's minus f of x0, and we just found what f of x0 is equal to, right? What's f of x0 equal to? 1 over h x naught to x naught plus h f of x0. So we have this exact same thing except f of x0 dt. Okay, so we use the linear property of integrals to combine these guys and get the integral from x0 to x0 plus h of f of t minus f of x0. Not an absolute value, but dt. All right, and then we use Theorem 522 to move the inequality inside the integral. 1 over h integral, h is positive, remember h is positive. We get the absolute value of f of t minus f of x naught dt, but this is less than epsilon. If, right, t naught minus x is less than delta, and we can make h small enough to make that happen, okay, since h is going to 0. And then what do we get here? This is equal to 1 over h epsilon times x sub 0 plus h minus x sub 0, once again by theorem 516. We use it again, and that's just equal to epsilon, because this is h, and that cancels that. Okay? So now by definition of limit, when this is less than delta, this is less than epsilon, we see the limit as h approaches 0 plus of big F of x 0 plus h. Move this up a little bit. So this difference quotient, this limit has to be f of x naught. And so this proves f prime of x naught exists, and f prime of x naught equals f of x naught. And then since f is given to be continuous, f is in big C of 1, big C1 of AB. And that's the proof of part 1. Okay, little QED, half QED for 1 anyway. Okay. And so we just use the continuity of f to get us this range here, and obviously same argument with different signs for the limit as x approaches, sorry, not as h approaches 0 from the left, right? We only did one side of the limit. Of this. But if I would have done that, then what would have happened? What would have happened is we would have had a negative sign here, because when we pull it out of the absolute value, this becomes negative. But then x naught is bigger than x naught plus h, and so you have to flip these, and you get it, the negative sign comes back in. So it works out the same. You get a couple of sign issues, but the signs cancel out, and you're okay. All right, so that's the proof of part 1. All right, the proof of part 2. The proof for part 2. All right, remember what part 2 says. Part 2 says that f has to be, little f is differentiable and f prime is integrable, then you get this thing, our basic fundamental theorem of calculus stuff that we're used to. All right, and for part 2, we need, really the big thing we need to use is mean value theorem and some sum stuff. That's what we're going to use. Okay, so we're going to let P be a partition, x sub 0, x1, x2, da da da, xn, be a partition of AB. Okay. Such that if we take the integral from a to b of f of t dt, and we take that and the difference between the sum j equals 1 to n of f prime of tj, this is a prime also, xj minus xj minus 1, that's less than epsilon, okay? And that's by the definition of integrability, right? Remember the definition of integrable, right? F prime is integrable. That's the Riemann sum definition of integrability. All right, I don't remember, I didn't write that one down, sorry. That's definition 517. Okay, that's definition 517 in your textbook. Okay, that's the Riemann Stieltjes definition of integration. The TJs thrown in there. Okay, remember the TJs are from TJ, I think we use a star, no, just TJ. Yeah, for TJ being some point in the x sub j minus 1 x sub j subinterval, right, with the partition. Okay, so that's just the definition. It's a big ugly one, but it's just the definition of that. Okay, now, however, by the mean value theorem, the basic mean value theorem, on the interval x sub j minus 1 to x sub j, there exists a c sub j in here, using a little bit different notation than he does, but that's okay. C sub j in here, such that what happens? Such that f prime at cj equals f of xj minus f of xj minus 1 over xj minus xj minus 1. All right, and one thing I need to make sure that you guys recognize, right? This is for any tj, right? This is true for any tj. That's the Riemann sum power. The Riemann sum power is that it doesn't matter which point you pick in here. This is true for any tj. And now guess what? We've got a cj that if I multiply both sides by the denominator, I get f prime of cj times xj minus xj minus 1 is equal to f of xj minus f of xj minus 1. So we're going to take this portion right here, we're going to take that guy, we're going to copy it over and come down here and say, so in oops, that is not what I wanted. Let's see if I can do this. There we go. All right, and I don't want this such that part. In fact, I don't want any of this really. I'm just going to steal this guy. Okay, so let's move him over. And I probably could have written that just as fast. But anyhow, so what do we got here? Here, this is equal to what? The sum j equals 1 to n, right? Of f of xj minus f of xj minus 1. Okay, because cj equal to tj is okay on every one of those subintervals, right? Because this was for any tj, and cj is a tj. So now, by telescoping series, what do we get? What's the sum look like? this sum is just f of x1 minus f of x0 plus f of x2 minus f of x1 plus f of x3 minus f of x2, da 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 da, right? So this is f of x1 minus f of x0 plus f of x2 minus f of x1 plus dot dot dot, right? So basically by telescoping you just end up with f of xn minus f of x0, everybody else cancels out, but what is xn? It's b. And what's x0? It's a. Right? So where did this come from? Where was this guy? I can replace that guy with it. So up here, we were looking at this definition. So this was the Riemann sum definition, right? So in this place, the sum f prime of tj, you can replace this with just f of b minus f of a. All right, so once again, let me see if I can do this. All right, we're going to cut. Oh, wait, I already copied it before, right? So never mind. It should just pop up again. Hey, all right. So what does that mean? That means we have, instead of this guy, we replace this guy with this guy, f of b minus f of a. So this here becomes f of b minus f of a. And that's exactly what we wanted to show, right? And since that's less than epsilon, that implies that the integral from a to b of f prime of t dt is actually equal to f of b minus f of a, which was the fundamental theorem of calculus part 2. Okay? And so that was true for the b. Okay, we could have just as easily we could show that the integral from a to x of f prime of t dt is equal to f of x minus f of a for any choice of x in AB. Right, we just worked with the outside guy, but if you stopped anywhere, you could just subdivide and stop, okay? And so that doesn't change anything. And so we've got the theorem. And that's it. So hopefully you know how to use the fundamental theorems, but I wanted to at least take some time and show you guys where the proof came from. And hopefully that makes sense. Take a look at your book and follow it through, and you should be good. We'll see you later. Thanks.